Chapter 5 Torsion. In this example, we want to review an interesting problem in Chapter 5 Torsion, which includes a steel shaft and aluminum tube. So we have a hollowed aluminum tube, both connected to a fixed end at for example, at A and free at the other, which applied a torsional torque of T. This is our hollowed shaft, hollowed tube of aluminum, and inside the aluminum we do have a solid steel shaft. As you can see here, this is a steel shaft embedded in a outer tube of aluminum. I want to give the specification of a shear modulus for steel is 77 gigapascal, shear modulus for aluminum 27, allowable stress is 120 megapascal for steel shaft, and likewise 70 for aluminum tube. Want to know what is the maximum torsional torque of T, which we can apply at the free end of our problem. Let's start our solution. So we need to use equilibrium equation, compatibility of displacement, and load displacement to go through all these steps to solve our problem, because this is kind of determinate structure. So first of all, equilibrium equation gives us the summation of torsional torque in each part should be equal to the total torsional torque of T. Compatibility of displacement says if they are embedded inside each other, so there is no way to have the same amount of rotation for both of them, because there is no way that they can move separately. So that's compatibility of displacement. If something is embedded in the other, so phi of steel, angle of twist or rotation of steel is equal to angle of twist of aluminum shaft tube. And the load displacement gives us phi in terms of a angle of twist is TL or GJ. So T for steel, L in both of them are the same, like 500 5 meter. G steel over J steel, polar moment of inertia of each of the material time with modulus of rigidity of each of them, and should be equal to the other side. So these are three equations we need to solve our problem. Let's calculate the polar moment of inertia, moment of inertia for each part. So J for aluminum tube is a half of pi times C to the force minus C1 outer to the force minus inner to the force, radius then millimeters, inches base of your unit to the force, and it just gives us this amount, something 6 meter to the force. And if you, and also with the shear modulus of this aluminum, each material is provided. For example, for aluminum is just 27 gigapascal. If you do the same for the other material, it just gives you J of aluminum, J for steel, internal solid shaft, steel, solid steel shaft inside the tube, and G steel, G for aluminum steel is 77 gigapascal. equalize these two equations, it just gives you, cancel out these two terms, the length is the same, which is for each of them. Place the numeric value for G, J, for example, J for aluminum is a 2 point, almost 2 to negative 10 to negative 6 times 27, and do the same for a steel, which is here 77 for rigidity modulus. It just gives you a relation between the portions. So have equilibrium equation which says both of them should equal to the total T, and now we have a relation between them, so we can now solve our problem. So let's assume we need to see which material reaches to its allowable stress first or sooner. Let's assume the controlling part is the aluminum shaft. So just assume aluminum is controlling in terms of strain. So is the critical material, then we need to verify it. So in that terms, tau is equal to tau is Tc over J. So likewise, tau maximum for is T of aluminum times C2, because maximum works with the outer layer. So that's a C2 because C2 is greater than C1. Tau max of aluminum is T of torsion of aluminum times C2, which is the larger radius because of tau max here, toward C2, larger radius because of tau max over J aluminum. And we replace tau max of aluminum with the problem statement of tau allowable of 70. Then the only unknown here is tau, and the radius is also 38 millimeters, as you can see here. Outer radius for aluminum shaft is 38 millimeters, which replaces for C2. So the only J we already calculate J for aluminum, which is 2 point something. And if you replace that, it just gives you a tau aluminum is equal to value of 3690 Newton, 3690,690 Newton times meter for share of aluminum from a unknown torsional torque, because we are looking at this unknown maximum allowable unknown torque. So if we just replace the equation, if you remember the relation between the two torsions between compatibility phi aluminum is equal to phi steel, just gives us this equation. We may expand it, and if there is this relation between them, if we have one of them, we can easily calculate, have the aluminum one, can easily calculate the steel. The only part here, so it just gives us a proportional torque for steel is a 3,200 by 32.5 newtons. But if you remember, we just assumed aluminum is controlling. We just need to double check to see if by this assumption the steel is not passing the maximum allowable shear stress. So if you replace that in the equation, so tau maximum for the steel, which we are going to calculate a calculated tau maximum, and compare that with 120 for tau allowable steel, which is 100. So if you do that, if you do the math, it just gives you 131, which is definitely larger than 100. So the assumption of the aluminum is controlling was not right. The this is not this condition. So definitely if aluminum is not controlling, then definitely steel is the controlling part. So cause the allowable stress of 120, this is 120 megapascal for steel is exceeded. The assumption is not correct, so because T calculated T power for steel is 131, and that's bigger than allowable amount for steel, allowable shear for steel based of problem statement. So the assumption of our initial assumption was correct, is not right, and now we know steel is controlled. Now, if the aluminum, we have a aluminum tube, hollow tube, and a steel rod. So if this aluminum is not controlling, then steel is controlling. So we can easily, by replacing tau maximum for the steel, no assumption, can calculate, and this assumption is correct because one of them is controlled. If the first one is not controlling, definitely the second one is controlling. If you replace tau is equal to Tc over J, replace that by 120 Pascal. Our problem statement just gives us the share of steel is equal to 2950 Newton meter share of steel. If we have the share of steel and we have the relation between two portion, we can easily calculate the other one. So based off this equation, these two equations, we can calculate the share of aluminum from the torsion. And if we add the two share, we get the total amount of T, which is 6.305 kilonewton meters, which is the maximum applied torsional torque at the free end of this shaft. There is no need to check if the other material, because this time we just assume that the steel is controlling. There is no need to check if aluminum is passing or exceeding the allowable, because we first take an assumption of aluminum is controlling. If aluminum is not controlling, definitely steel is controlling. But yet, if you want to be checking for the tau maximum to be more confident, you can, based off tau aluminum, J aluminum, can calculate tau maximum, a new tau maximum for aluminum, to see if that's bigger or smaller than tau allowable for aluminum or not. And that should be definitely less than 70. Let's see how it goes. If you place a 33.75 times the outer radius, because that's tau maximum for shaft, polar moment of inertia of inertia just gives you, for aluminum, it just gives you 64.03 megapascal, which is definitely less than 70 megapascal, which is the acceptable or allowable stress for the aluminum. And done also be checking, but there is no need. It's just a extra part. If you want to double check your problem, you can do this checking. Let's see if we can solve this problem any easier. Yes, we can do. Parallel condition gives us a far better, easier solution. So as soon as we do know the steel core shaft inside the and aluminum tubes are in parallel. Why in parallel? Because phi of steel is equal to phi of aluminum. It means the displacement of both of them are equal, and delta equal is the condition of parallel condition. So at the same time, we do know both of them should T steel plus torsion of steel plus torsion of aluminum total T. We have to calculate again J, and we are provided with G shear modulus. So if you calculate both of these, like was previous solution, we do calculate polar moment of inertia for both of them. And then portion of steel is torsional stiffness of steel over the total stiffness. So that's Gj over L. So we have Gj over L is Ea over axial stiffness, or we can say shearing stiffness, which is axial stiffness. So if you enter the stiffness of steel, if you want to calculate share of steel, that says in parallel condition, the ratio of stiffness of that material to the total stiffness times the total load, which is a torsion here, it just gives us, you can easily cancel out the part, the length part, and you can easily rewrite it like this equation. So if you do that, it just gives you torsion of steel is 0.166 times the total torsion. Now we need to see which material is controlled. So in design, we are interested in a smaller deformation. Smaller deformation, that's our concept. So the material, the one with the smaller shearing strain, that's gamma, because we are looking the a shear stress now, right now, that's the controlling. Tau allowable is G times gamma allowable, and that's the Hooke's law in terms of shear. Tau is equal to G times gamma, and the smaller the gamma, that's the controlling. Gamma for steel is tau of steel, which is allowable tau 120 times 10 to 6 is a problem statement times G of steel. Again, that's provided, just gives us 1.610 negative cubed. And gamma for aluminum just gives you 59. So definitely the smaller one is 1 point. Steel is controlling. You can easily see which material is controlling. Even this one is easier because we don't do any assumption for that. Like this problem, we just directly calculate the gamma for each of them, shearing the strain for them, and the smaller the strain, the controlling the material. Because and tau for steel is 0.66 times the total, and tau is Tc over J. If steel is controlling, you easily calculate, replace the share of steel with this equation. If you do so, it just gives you a tau of steel, which is equal to point almost 50 T is this equation, and it just gives you the total torsion of 6.32 kilonewtons, which if you remember the previous part, we just get the total amount 6.32 325 kilonewtons, and they are close enough, they're almost the same. Thank you. Solve more problems.